Hello and welcome. Here we shall talk about finite fields, finite geometries, the 25-point model, the 16-point model, and the connection to Latin squares. Very quickly, this is not totally a self-contained lecture. I'm assuming you know already some things. Let's go. Here's what we have here. We have this object called Z5. What is Z5? It is a so-called finite field. So it's finite. In fact, it is a set of size 5. The four elements are 0, 1, 2, 3, and 4. And you can, philosophically, you can think of these as just the regular numbers, 0, 1, 2, 3, or 4, or you can think of them as some sort of special new objects with very similar names. Anyway, I'm here to tell you how these numbers relate to each other. In particular, I shall define an addition-like operation on them, and I shall define a multiplication-like object on them. So here's a chart, and here are the 5 elements going this way, and here are the 5 elements going this way, and I'm now just going to tell you what happens when you perform this binary operation on these two numbers. It's just like a binary function. Well, okay, it works exactly how you would expect. 0 plus 0 is 0, 0 plus 1 is 1, 0 plus 2 is 2, 0 plus 3 is 3, 0 plus 4 is 4. And it also works this way as well. So 0 plus 1 is 1, 0 plus 2 is 2, 0 plus 3 is 3, 0 plus 4 is 4. In fact, addition is commutative. In other words, it doesn't matter in which order you add the two numbers. Okay, what's 1 plus 1? It's just 2. So far these numbers are acting exactly like normal. 1 plus 2 is 3, 1 plus 3 is 4, but 1 plus 4, well, in normal numbers that would be 5, but we have no 5 in our system, and so we just kind of carry over. 1 plus 4, we say, is 0. All right, so if you know modular arithmetic, kind of a prerequisite for this, then these are all of the possible remainders when dividing by 5, and the sort of rule, so to speak, for adding two numbers is you do it mod 5. So you add two numbers up, and then you take the remainder. If you treat these numbers like normal numbers, then when you add them up, you get a normal number, and then you take the remainder after dividing by 5. Okay, so now going a lot more quickly, 2 plus 1 is 3, 2 plus 2 is 4, 2 plus 3 is 6, but 6 is equivalent to 1. 2 plus 3 is 5, I should say, and 2 plus 3 is 5, and 5 is just equivalent to 0 mod 5. 2 plus 4 is 6, which is equivalent to 1 mod 5. 3 plus 1 is 4. 3 plus 2 is 5, but that's 0. 3 plus 3 is 1. 3 plus 4 is 2. 4 plus 1 is 0. 4 plus 2 is 1. 4 plus 3 is 2. And 4 plus 4 is 8, which is 3. Okay, so this is the addition table. We can notice some things about this table. First of all, this addition operation is closed under this set. That is to say, if you take any two elements whatsoever from this set and add them together according to this rule for addition, you always get a number that is in this set. Also, as I already mentioned, the addition is commutative. It doesn't matter in what order you add them, and that can be seen by the table being symmetric with respect to some diagonal or something like that. Also, it's associative. You can just trust me on that, or you can just think about it for a second. Of course, it's associative. It doesn't matter whether you do A plus B plus C or A plus B plus C. This is too much detail. It's just associative because duh. And also, there is an identity element. The identity element for addition is 0. What does it mean to be an identity element? Well, 0 plus anything just is that thing. Also, every number has an additive inverse. For example, since the additive identity element is 0, then for any number there has to be a number that you add to it to get 0. So 3 plus what is 0? Well, 3 plus 2 is 0. 4 plus what is 0? Well, 4 plus 1 is 0. So 4 and 1 are additive inverses of each other. You can see that this is true by seeing that there exists a 0 in every single row and there exists a 0 in every single column. That is to say, there's always something you can add to any number to make 0. Okay, so therefore this constitutes a group under the operation of addition because it's closed, associative, there's an identity element, every number has an inverse, and in addition it's commutative, so it's a commutative group, an abelian group. Okay, going too slowly. We continue. There's also a multiplication table. How does that work? Okay, here with less commentary, even though this is harder, I'll just say that you also just do it mod 5. So 0 times anything is 0. So we fill in these, and then 1 times 1 is 1, 1 times 2 is just 2, that's 3, that's 4. Here we get 2, 4, 2 times 3 is 6, but that's just 1, 2 times 4 is 8, so that's just 3, and 3 times 1 is 3, 3 times 2 is 6, but that's just 1, 3 times 3 is 9, but that's just 4, 3 times 4 is 12, but that's just 2, 4 times 1 is 4, 4 times 2 is 3, 4 times 3 is 12, but that's just 2, and 4 times 4 is 16, but that's just 1. Okay, so again, we have this operation, multiplication, which is closed. If you multiply together any two numbers from this set, then you always get another element from this set. It is commutative. It is associative. Again, it's kind of just obviously associative because regular multiplication is associative. So if these were normal numbers, then these two would be equal. But here, since you're just taking the remainders mod 5 after doing normal multiplication, then it's clear here that this particular artificial multiplication system is also associative. Also, there is an identity element for multiplication that is 1. When you multiply any number by 1, it leaves it unchanged, as can be seen from this row and this column. So 1 is the identity element, and now every number except 0, which is the additive identity element, has a multiplicative inverse. And that can be seen, well, okay, take 2 for example. The multiplicative identity element is 1, so there has to be a number that you multiply 2 by to get 1, and here you multiply 2 by 3 to get 1. So 2 and 3, we say, are multiplicative inverses of each other because of the two numbers that you have to multiply each other by to get back to 1, the multiplicative identity. Similarly, if you multiply 4 is its own inverse, because 4 is the number you have to multiply 4 by to get 1, and 1 is its own inverse, and 0 doesn't have an inverse. Okay, so if you put this all together, these are all the requirements that you need to have for a field. There is a binary operation addition, a binary operation multiplication, and those two operations are each individually closed under that operation, associative, commutative. There's an identity element for addition, there's an identity element for multiplication. Every number has an additive inverse. Every number except for 0 has a multiplicative inverse. And then they are related to each other by the distributive property. Okay, so you can just trust me that this satisfies all the field axioms. This is called a finite field. And here we say this is a finite field of order 5. And the finite field of order 5 is the finite field with 5 elements. Whenever n is a prime number, there exists a finite field for that number. And in fact, any other finite field of order 5 is essentially just this one. Possibly you've given the elements of that field different names, but they are basically the exact same structure. We say that they're isomorphic. Whenever there's a prime number, there is a finite field of that order, and one way to construct the finite field of a prime size is by doing it just like this. It's kind of obvious. Okay, I'm spending too much time on the easy stuff. Let's get to the actual assignment. The actual assignment says, part A, the very first thing that you were supposed to do was find the line 3x plus 4y equals 1. Okay, so here what we have now is a coordinate system in which I plan to have points here. In fact, there are 25 points, and these 25 points have been labeled with ordered pairs based in the normal kind of way, taken from this set. So what I want to do is I want to find all the points, all the ordered pairs x comma y, which satisfy this equation. Okay, so there are a lot of ways to do this. The sort of tedious way to do this is to just do it. If you didn't know anything and you had no experience going in, you could just plug in the first number, like 0, into this equation. And if x is 0, then 3 times 0 is 0. And so this is equivalent to 4y equaling 1. Well, what times 4 is 1? Answer 4. So that's how I know that the point 0, 4 is one of the points of my system. I'll put a little square around that. I think I'm gonna run out of time before the good stuff, but oh well. Okay, continuing. Plug in 1. If you plug in 1 for x, then you get that x is 1, 3 times 1 is 3. So you get 3 plus 4y has to equal 1. Well, 3 plus what equals 1? Answer 3. 3 plus 3 is 1 in this world. So, therefore, this is true if and only if 4y is 3, and what times 4 gives you 3? Answer 2. So from this we learn that y must be 2. And thus we get this point. I feel I've made a mistake somehow. Let me try this again. If x is 1, 3 plus what is 1? 3 plus 3 is 1. And 2 times, I guess this is right. Y is 2, so you get the point 1, comma 2. Oh yeah, sure, everything's fine. Here it is, boom. That is the point 1, comma 2, marked with a purple square. Okay, and we just do this 3 more times. So let's go a little bit faster. If you plug in 2 for x here, you get 3 times 2 is 6, but 6 is just 1. So you get 1 plus 4y equals 1. Well, that's true only when 4y equals 0, but that's true only when y is 0. So I get 2 comma 0, and there it is. And then if I plug in 3 for x, I get 3 times 3 is 9, but 9 is
Good
just
morning,
4.
Blair. Please pardon the interruption.
Right.
Today is senior
4
commit
plus
day, and
4y
activities will be held in
equals
the senior courtyard
1.
during lunch. Today,
4
please
plus
also
what
seniors
is
come
1?
and fill out complete the senior survey
3.
and get an ice cream. Thanks,
No,
have a great
sorry.
day.
4 plus 2 is 1. So this is true only when 4y equals 2. 4 plus 2 is 6, which is just 1. Okay, well 4 times what gives you 2? Answer 4 times 3 is 12, which is 2. So this is true when y is 3. So therefore, we know that when x is 3, y is 3. Okay, this is like very tedious. But anyway, there's only one more to go. If x is 4, 3 times 4 is 12, but that's just 2. So you get 2 plus 4y equals 1. But 2 plus what equals 1? 2 plus 4 is 6, which is 1. So, yeah. So this is true only when 4y equals 4, which is true only when y equals 1. So that's how we get the fifth point, which is 4 comma 1. Okay, so this was done with basically no understanding whatsoever. Was there kind of a better way to do this problem? Yeah, definitely there was. The better way to do this problem, in my opinion, is to take the equation 3x plus 4y equals 1 and make it look more like a normal line equation. Well, in particular, I like my formulas to look like y equals mx plus b because I know what the slope is and what the y-intercept is. So, I don't want this to be a 4y, I want this to be a y. Well, I just chose to, I don't know if this is the easiest thing to do or not, but I just chose to multiply both sides of this equation by 4. If you multiply both sides of this equation by 4, you get 4 times 3 is 12, but then that's just 2x. 4 times 4 is 16, so that's just y equals 4. So now you get this equation, which you can either write as y equals negative 2x plus 4, or if you prefer, negative 2, if you don't like negative 2 for some reason, then you can think of it as y equals 3x plus 4, since 3 and 2 are equivalent mod 5. And now, looking back at this picture, if you look at these 5 purple squares, they form a line. It's a discrete line because it's a line consisting of only a finite number of points, 5 points. And what can I say about this line? Well, it has slope negative 2, as can kind of be seen by drawing the line like this. Slope negative 2 and y-intercept 4. So this is kind of beautiful. And if you think of the line as continuing downward, then it kind of like wraps. But if you also want to think of it as having a slope of 3, then you can just equally well go like this and say slope 3 and then back down to 2 again. So, okay, these dots might be sort of confusing or not, but or these dashed lines rather, but that is one of the lines in our model. It's the line 3x plus 4y equals 1. So I'll put a little purple square next to this, purple square, purple square. Okay, great. What else? Well, this is just the tip of the iceberg or something. Oh man, I've completely ruined this video because the bell's about to ring and everyone's supposed to come. But there are 4 more lines. And those 4 more lines are the lines, well, in addition to y equals 3x plus 4, there is just y equals, well, I'll just write it as negative 2x. There's y equals negative 2x plus 1. There's y equals negative 2x plus 2. And there's y equals negative 2x plus 3. And now we can just kind of do these really fast. So on my thing, I did it with a circle. So I'll make a little red circle for the line y equals negative 2x plus 3. Well, circle, slope is negative 2, slope is 3, slope is negative 2, and slope is, no, I've made a mistake, negative 2, 3 goes up here, up 3 and over 1, slope negative 2, and slope negative 2. So these 5 circular dots constitute the 5 points that satisfy this line y equals negative 2x plus 3. You can like check that yourself if you don't believe me. Then let's see, we can do y equals, I'll make a little triangle for y equals negative 2x plus 2. That is this one. It's the line with slope negative 2, also known as slope 3, but with y-intercept 2. So now I go up 3 over 1, slope negative 2, and slope 3. And this line consisting of these 5 green triangles is this line y equals negative 2x plus 2. Okay, 2 more. I will use the blue star symbol to refer to the line y equals negative 2x plus 1. That's the line with slope negative 2, but y-intercept 1. I go up 1, 2, 3, down negative 2, negative 2, and up 3. So finally, I will make a little pink heart for the line y equals negative 2x, which is the line with slope negative 2, also known as slope 3, and y-intercept 0, so it looks like this. Okay, so what do we have here? We have a set of 5 lines. There are the 4 mentioned here, and there's the one we already did kind of in the warm-up, y equals negative 2x plus 4, which I did with a purple square. And these 5 lines together cut through the 25 points of this geometric model. It's a finite affine model of order 5. There are thus 5 squared equals 25 points. There are 5 lines that I've presented here. Each line passes through 5 points exactly, and all of these lines are parallel to each other because they all have slope negative 2 or slope 3. Okay, and from this we can make a Latin square. The Latin square kind of associated with this is the one in which, I'm going to let the people in who are outside my door. It's the one associated with, well, I'll just say the line of 4s, the purple lines are these, slope negative 2, also known as slope 3. This is like a 3, slope negative 2, also known as slope 3. Then there's the green one, slope negative 2, also known as slope 3. The blue one, slope 3, also known as slope negative 2. And finally, in pink, instead of calling it 0, I'll call it 5, because that's more standard. Slope 3, slope negative 2, slope 3, slope negative 2. Okay, and maybe I'll just stop there. Goodbye.